Welcome back, ladies and gentlemen, to another video with Mr. Kenton. And in light of the video that we just produced that was looking at acids and bases, I wanted to provide some context and maybe just walk you through a couple of practices of how to identify conjugate acids and bases using that Bronsted Lowry definition. But then also wanted you to be able to write reactions for that, and also to kind of explain kind of the last bullet that's on the slide, which talks about the equilibrium is going to favor the side with the strongest acid and producing the strongest acid donating its proton to form the strongest base. I wanted to provide some context for all of those things, and so I'm going to be making a video of me just walking through some practice things to hopefully give you some context for how to address those questions. And I'm going to work from the simplest things and then work my way through more difficult things. And so you got two questions that are before you. Let's just look at the first one. It says, what is the conjugate base of the following acids? Right? And so for an acid, they give us HClO4, H2S, pH4+, and HCO3-. Now, if you remember using the Bronsted Lowry definition of an acid is any substance that can donate a hydrogen, right? And so if that is the case, then when we start to look at each of these, the conjugate base for HClO4 is simply going to be ClO4-, right? The perchlorate ion. So ClO4- would be the conjugate base of HClO4, right? Because ClO4- has lost a proton, right? It is the substance that was formed as a result of perchloric acid losing its proton. Now, if we look at the next one with H2S, if H2S were to lose a proton, we would be left with HS-, right? HS- would represent the conjugate base of H2S, right? If we look at pH4+, if it loses a proton, is going to go to pH3, right? No longer has that positive charge, and so we get the formation of pH3. That would be our conjugate base to pH4+. And then lastly, for HCO3-, if HCO3- were to donate a proton, if it were to lose its H, it would lead to the formation of CO3 2-. So kind of how I've written it, the conjugate or the acid is on the top and its conjugate base is written directly below it, right? And again, the thing that they all have in common is that each of those acids donated a proton to lead to the formation of the new ion or molecule that we see that's listed there. Okay. Now for the second question, what is the conjugate acid of the following bases? Now they're telling us, using the Bronsted Lowry definition, that each of these four substances that we've written are bases. And from that, we know that the Bronsted Lowry definition says that bases gain protons. So if each of those ions or molecules are allowed to gain a proton, we would form a conjugate acid. So for example, if Cn- were to gain a proton, it's going to become HCN. That would be the conjugate base, the conjugate acid for the cyanide ion, hydrocyanic acid. Right? If we look at sulfate, SO4 2-, if it gains a proton, its conjugate acid would be HSO4-, right? Because it's gained a proton, and so its conjugate acid would be HSO4-. For water, if water were to gain a proton, we'd get the formation of our hydronium ion. We got H3O+. So when water acts as a base, its conjugate acid is hydronium ion. And then lastly, we've got HCO3-. If it gains a proton, it's going to be changed into carbonic acid, H2CO3. right? And so, again, we've got our bases on the top for question number 2. So cyanide, sulfate, water, and hydrogen carbonate. And then we've got their conjugate acids that are listed below them. HCN, HSO4 1-, H3O+, and H2CO3, right? And another thing that you might even notice within that, notice that we had HCO3 listed as an acid, and it's listed as a base. So that means that HCO3 is another substance that's amphoteric. It can be either a Bronsted Lowry acid or Bronsted Lowry base. Okay, now I hope that makes sense. The next thing I want us to think about would be being able to write an equation to kind of represent how a substance would behave as either an acid or a base. Okay, so I'm going to make this disappear. So if you need this, you're going to need to go back to it, just pause the video and rewatch it. But I'm going to make this disappear now. And so let's say that we're given the question. We're told that hydrogen sulfite ion, HSO3-, is amphoteric, right? So they tell us that it's amphoteric, and like we just saw previously, that means it can behave as an acid or a base. And it says, all right, here's the two things that we want to do. We want to be able to write an equation for the reaction of HSO3, the hydrogen sulfite ion, where it behaves with water as an acid, and how it behaves as a base. And in the process, we want to identify what are the conjugate acid-base pairs. Okay, so let's deal with the first one. Let's show it reaction A, where we're showing HSO3- as an acid, right? So we're told we've got HSO3- AQ. It's going to be reacting with liquid water. Now, if it's an acid, certainly it's a weak acid. It's not on our list, so we have to represent it with equilibrium. So I'm going to write double arrows in here. That's what the double arrows mean. The reaction's at equilibrium. And so if HSO3- is going to behave as an acid, that means that it's going to donate a proton to water. So that means we're going to be left with SO3 AQ plus H3O+ AQ. That would be the reaction that represents hydrogen sulfite anion as an acid, right? And I guess let me change some colors here to identify the acid-base pairs, right? So let's go with some yellow, right? So HSO3, this is an acid, and then SO3 would be the conjugate base. I'm just going to abbreviate that CB. Our bases in this case, this is our base, and H3O+ is our conjugate acid, right? Hopefully that makes sense. All right. Now, the next piece, let's show an equation or show a reaction where HSO3- is a base when it's placed in water. So we got the same things. We got HSO3- AQ plus H2O is a liquid. It's going to be at equilibrium again. And now if HSO3 is going to behave as a base, that means that water is going to be the one that's donating its proton, right? So then we're going to get the formation of H2SO3, which is sulfurous acid, plus hydroxide ion. Now again, to kind of think through that, right, if we want to identify what substance was our acid and its conjugate base and which substance was a base and its conjugate acid, since water was our proton donor, that means that water was an acid and hydroxide is the conjugate base. Likewise, right, HSO3 minus, that's our base, and our H2SO3 is our conjugate acid. And again, hopefully what you're able to kind of see here from the equations, we're seeing how both of those work out, but the key piece here, because we're dealing with weak acids and weak bases, make sure we include the double arrows to represent equilibrium processes that are taking place. All right. So hopefully that makes sense, which is going to lead me to my last point, where if you remember from the PowerPoint, I mentioned that these conjugate acid-base pairs are going to form in such a way that it's going to favor the transfer of the proton to the stronger base. And you might have been thinking, well, Mr. Kenton, that's a really vague question. So how do we determine which way this is going to work out? And so hopefully when we look at this process, it's going to make a lot of sense to you. So, you know, let's say that we're given the following reaction. We've got HSO4 minus AQ plus CO3 2 minus AQ is at equilibrium, and it's going to form, or the reaction would be sulfate SO4 2 minus AQ plus HCO3 minus AQ. Okay, so this is our reaction. And the question they're asking us is, which side of the reaction is favored? All right. So it's kind of a broad question, you know, which side of the reaction is favored? How do we figure that out? And I guess I kind of want to break down what the question means, right? So in an equilibrium process, we know that we're going to be moving in the forward and the reverse direction. However, at equilibrium, that doesn't mean that we're going to have the same amounts of everything on both sides. What it means is that one side of the reaction is going to have possibly more reactants or more products, depending on which side is favored. And so when they're asking us this question, they're saying, which side is going to be favored? What are we going to be most likely to see at the particle level if we were to analyze a solution from this reaction? Would we anticipate seeing more HSO4 minus and CO3 2 minus? Or would we see more sulfate and HCO3 minus at the end result once equilibrium had been established? Okay, and so, you know, the thing that we're going to have to identify is what's the relationship between all of these different substances that are present. Okay, and so, or maybe the question becomes, which of the acids that we have present here are we going to see, or that we would say, which acid is stronger, right? And so when you look at this, the two substances that can behave as acids would be our HSO4 minus and our HCO3 minus. Now, if you're remembering, why can they behave as acids? Because they have protons that are available to be donated. So then when we look at kind of that chart that's given to you, it's on page 618. It was in that last slide of the PowerPoint. You're going to want to take a look at the acids and bases there. So we're going to want to look at HSO4 minus, and we're going to want to look at HCO3 minus, right? And so when we look at this, we see that HSO4 minus is a much stronger acid than HCO3 minus, right? And so we could even look at it from the perspective of the base as well. If you look at carbonate versus SO4 2 minus, these are our two bases that are in this reaction. So when you look at it, carbonate, CO3 2-, is a much stronger base than sulfate. So what that's going to mean is that carbonate is going to want to accept a proton way more than sulfate is. Likewise, HSO4- is going to be way more likely to donate a proton than HCO3- is going to be. So then if we were to determine what are our acids and bases in this particular reaction, we would say that HSO4-, I'm just going to kind of write this underneath here. HSO4- would be our acid. Carbonate would be our base, which means that SO4 2- is the conjugate base, and HCO3- is the conjugate acid. Now, back to the question. So which side of the equilibrium of the reaction is going to be favored after identifying that HSO4 is the acid, this is the base, and conjugate acid? Well, if we've understood this correctly, that means that this reaction is going to favor the products. So this reaction favors the products. So this reaction is going to favor moving in the forward direction, making sulfate ions and HCO3- ions. Okay, I hope that helps. If you do have any other questions about anything that I went over in these problems, please don't hesitate to ask. I'd love to be able to help you guys out, look at other problems, look at other things. But hopefully this provides you guys with some clarity. Thank you so much for watching this. Hope you have a great day, and I'll see you guys again soon.